In the last video, we talked about insertion sort. In this one, we're going to tackle the next sorting algorithm that we have in our n squared arsenal, and that's selection sort. So just like in insertion sort, we're always going to have a portion of the array that's already sorted and a portion that's currently unsorted. So here, our little mini pseudocode algorithm over on the side, it says that starting at the end of the array, we're going to move a counter or a pointer I from the end all the way to the beginning, each by one step. And each time we're going to find the maximum. Here it's in 0 to I. And really what that means is that we're finding the maximum in the unsorted portion of the unsorted portion of the array, and then we're going to swap that maximum with the last element, so with element I. Right? So initially we start with our entire array unsorted, and our I is the last element, array length minus 1. And we're going to go through and we're going to find the maximum. Here it's 18. And we're going to swap 18 with 2. And what that does is that actually puts 18 in the correct place. So, unlike insertion sort, there's no moving things around once they're in the right place. So 18 is here, and it's going to stay here for, all the way to the final solution. And now 2 is in some other location, and we'll deal with it a little bit later. So then the next one is to move I back by 1. So now I is array length minus 2. And we're going to find the maximum in this entire unsorted part of the array. The maximum is 15. So we're going to swap those two values. And now 15 and 18 are both correctly sorted, and they're in the location that they're going to be in the final solution. So we're going to do that one more time. Figure out that 12 and 2 need to be swapped. And now the final 3 elements are correct. Then we get to 8. And from 8, we look through the rest of the elements. And we figure out that actually 8 is both the element that we need to update and the max. Well, we need to swap something with itself, which means we don't actually do anything, right? So 8 is in the correct place. And then we'll swap 7 and 3. 3 is in the correct place, and we now know, right, that 2 has to be in the right place, right? There's only one element left. It has to be the maximum. So really, we don't need to go all the way to, so here we're saying I goes to 0. Really, we could stop at 1. So we could say I is greater than 0, right? Because that final element, we know, once we get to that point, it has to be in the right place. Okay, so the last thing is to take the pseudocode that we had on the last slide and turn it into a little bit more developed code. And you can see here, basically what we're doing is we're first looping over the array, just like we said before, from the back to the front. And again, here, this could actually be I greater than 0, right? Because we don't need to sort that last element. I minus minus. We're setting the initial index of the maximum to 0, right? If the thing in the 0th index is the maximum, then nothing actually ever changes. If it's not, then we'll update it later. And then we're going to go through from j equals 1 to I and check to see if the element that's in index j is greater than what we already think is the maximum. If it is, then j is actually the maximum that we've seen so far. We update it and we keep going. The final thing to do is, once we've found the maximum, is swap these two. And remember, a swap is a constant time operation, but it takes 3 steps to do it, right? So then the final question is, what's the running time of this algorithm? Well, this inside loop, right? Inside loop runs from 0 or from 1 to I, which means its running time is I. So it's dependent on the value of the outside loop. And the outside loop runs n times. So we have our good friend the sum from 0 to n of I, which we know is n squared. Right? That's the worst case running time. So what's the best case running time? So worst. If we change the order of the input, does it actually change how much time it takes us to run this algorithm? No. It's also the best case. Because in every iteration that we go through, we're still always going to be checking to see if that last element is the max. And we can't find the max in an unsorted array without doing a linear scan. So this n squared is both our best case running time and our worst case.